Hey there, welcome to part 1 of Graph Theory with Python. In today's video, we're going to be solving a historical problem called the Königsberg Bridge problem, which really represents the roots of the branch that we now call graph theory. This problem was posed to a mathematician named Leonhard Euler in the early 1700s, and he dismissed it as not even being mathematics and not worthy of his time as a mathematician. But later he solved the problem and submitted his solution to an academy and published a paper about it. So something must have inspired him to solve it. So let's take a look at the problem and why Euler thought it wasn't even worth his time. Here's a map of the city of Königsberg circa 1613, about 100 years before Euler heard about the problem. It's situated south of the Baltic Sea on a river called Pregel, and you can see the river runs through the city. Here's the river here, and traces a path that divides the city into 4 separate areas. We have an area called A, area called B, area called C, and an area called D. If we zoom in a little bit, we can see there's 7 bridges spanning the river and connecting the various areas of the city. For example, here's one, here's another one, here's the 3rd bridge, the 4th bridge, Bridge 6, and Bridge 7. Königsberg was a wealthy city in the 1700s, and there were lots of wealthy merchants that lived in the city. One of the things that they reportedly liked to do on Sunday afternoons was go for walks around the city. And at some point, one of the townspeople came up with a puzzle, I guess to add a little bit of fun to their Sunday walks. The puzzle was, can you walk around the city in such a way that you cross each of the 7 bridges exactly once? So for example, if we start here, we could come across this bridge, then cross this one, work our way back over and cross this bridge, work our way through town and cross this one, then cross this bridge, and then we're stuck. And we still have 2 bridges that we didn't cross. Now, after repeated attempts, no one in the town was able to solve the puzzle or prove that it was impossible to do. In 1736, the mayor of a neighboring town called Danzig wrote to Euler and mentioned this problem to him. He said, "It would prove to be an outstanding example of the calculus of position, worthy of your great genius." Euler responded to the letter with a little bit of arrogance and said, "This type of solution bears little relationship to mathematics, and I do not understand why you expect a mathematician to produce it, rather than anyone else, for the solution is based on reason alone, and its discovery does not depend on any mathematical principle. Because of this, I do not know why even questions which bear so little relationship to mathematics are solved more quickly by mathematicians than by others. In the meantime, most noble sir, you have assigned this question to the geometry of position, but I am ignorant as to what this new discipline involves, and as to which types of problems Leibniz expected to see expressed in this way." So there's a couple things going on here. First, we see that Euler just blows this off as not even worthy of himself or really any mathematician. The second thing is this mention of a calculus of position or a geometry of position. Now, this was a reformulation of classical geometry proposed by the philosopher and mathematician Gottfried Leibniz in the mid to late 1600s and early 1700s. And this is the same Leibniz you may have heard was in a battle with Newton over who first invented the calculus. It's also the same Leibniz that was lampooned by Voltaire in his story Candide for his take on the philosophical problem of evil. Now, Leibniz wrote a huge body of work on what he called the analysis of position. He never published any of it, and that was for a couple of reasons. He received some ridicule from his contemporaries about this idea of the geometry of position, and second of all, he wasn't able to ever successfully produce anything he considered worthwhile or of any value from the theory. The basic premise of the geometry of position was to reformulate geometry in such a way that it doesn't involve any calculation, any dependence on things like distance or measurement. And instead of focusing on things like equality, it instead focused on things like congruence and similarity of objects in space. Now, Leibniz wrote a lot about this, and like I said, he never published any of it. So Euler, or even the mayor of Danzig, they could only have known about this from correspondence that either they had with Leibniz themselves or from hearsay talking with other mathematicians. Now, the Königsberg Bridge problem clearly stuck with Euler because it wasn't too much later that he actually published a solution. The first reference that we have to Euler's solution is to a letter he wrote to an Italian mathematician named Giovanni Marinoni. And in that, he says, "A problem was posed to me about an island in the city of Königsberg surrounded by a river spanned by 7 bridges. And I was asked whether someone could traverse the separate bridges in a connected walk in such a way that each bridge is crossed only once. I was informed that hitherto no one had demonstrated the possibility of doing this, or shown that it is impossible. This question is so banal, but it seemed to me worthy of attention in that geometry, nor algebra, nor even the art of counting was sufficient to solve it. In view of this, it occurred to me to wonder whether it belonged to the geometry of position, which Leibniz had once so much longed for." And here's another example of Euler's arrogance. He says that it occurred to him that perhaps this belonged to the geometry of position that Leibniz had mentioned. But we know that the mayor of Danzig already mentioned this calculus of position, planting that seed in Euler's mind. He goes on to say that after some deliberation, I obtained a simple yet completely established rule with whose help one can immediately decide for all examples of this kind with any number of bridges and in any arrangement whether such a round trip is possible or not. Now, in Euler's paper with the solution to this problem, he mentions that it could have been solved exhaustively by just checking all possible paths through the city. He does dismiss this as laborious and also mentions that this is an impossible technique for configurations with lots and lots of bridges. But the original problem posed by the townspeople of Königsberg by today's standards is pretty simple, and you can use a computer to check things exhaustively. So before we jump into how Euler actually solved this problem, let's take a look at how we can use Python to solve the problem for us pretty quickly. In order to solve this problem with Python, the first thing we have to do is figure out how we're going to represent walks through the city. Now, on the right-hand side of the screen, I have a diagram of Königsberg that was used by Euler in his paper. He got rid of the streets, the buildings, and everything else that's cluttering up the map to just focus on the important parts. You have the river, the bridges, and you have the different land areas in the city. Here, the land areas are labeled with capital letters. A, B, C, and D. And bridges are labeled with lowercase letters. A, B, C, D, E, F, and G. Now let's take a walk through the city and show how we can represent it as a string in Python. We'll start with land area C, first cross bridge C, then bridge A, bridge B, bridge D, bridge G, and finally bridge E. We're going to represent the walk as a string. It starts with land area C, capital C, and first crosses the bridge lowercase c, which leads us to land area A. Then we cross bridge lowercase a, which takes us to land area B. Then cross bridge lowercase b, which puts us in A. Then bridge lowercase d, we're back at land area C. Then we cross bridge lowercase g, which puts us on land area D. And finally, we cross bridge lowercase e, putting us in land area A. So this gives us a representation of the walk as a Python string. And this is how we're going to represent walks in our program. In order to do this, we're going to first define a list of bridges. Now, the bridges in the diagram are represented with lowercase letters, but it's helpful to know which land area the bridge starts with and ends at. And picking which land area is the start of the bridge and which land area is the end of the bridge doesn't really matter. So we'll represent each bridge as a string with 3 characters. The uppercase letter of the land area that starts the bridge, then the lowercase letter representing the bridge, and the uppercase letter representing the terminal end of the bridge. So here we have uppercase A, lowercase a, uppercase b, and that corresponds to this bridge here. Uppercase a, lowercase b, uppercase b is this bridge, and we can keep going. Now that we have all 7 bridges represented as strings in a Python list, let's take a look at how we're going to build all possible walks using these bridges. What I've done here is defined a function called getWalksStartingFrom. This is going to generate all possible walks starting from a land area. We're also going to pass to that function the bridges that we defined in a list earlier. We'll use a list to keep track of all possible walks, and a function called makeWalks that we're going to call recursively to build up all of the walks starting from the area. What this function is going to do is take an initial area and everything that we've already walked up to that point, as well as the bridges crossed, and generate all the possible walks starting from that area. So initially, walked is none because we haven't walked anywhere. And if that's the case, we're just going to start with area. Now, area here is a string with a capital letter for one of the 4 land areas A, B, C, or D. And we're using the short circuiting of the OR operator here to either take walked if we've already got a string of everything we've walked, or that initial string area. Same thing for bridges crossed. If we have already crossed some bridges, then we're going to have a tuple of bridges that we've already crossed. Those are just the 3 character strings from the bridges list, or we'll start with an empty tuple. The first thing we need to do is get all available bridges from where we're standing. So we're currently standing on some area that we've passed to this function. We're going to take all bridges that contain the area in the bridge, right? So if we're starting on area A, we're looking for all bridges that contain a capital A, as long as that bridge has not already been crossed. So this will give us a list of all available bridges. Once we've got that list, we need to determine whether or not our walk has ended. In other words, whether or not we can continue walking. We do that by looking at whether or not there's anything in our available bridges list. So if this list is empty, that means that we're stuck. We've reached a point that we cannot go any further. There's no longer any bridges available to us to cross. And we're going to take the walked string and append it to our list of walks. Now, this walked string is going to look like that string representation of a walk that we saw earlier. So let's see how we're going to build that. For each bridge in our available bridges list, we're going to create what I call a crossing. And that is a string representation of the bridge that we're crossing now and the land area that we're crossing into. If we're starting on land area capital A and we're crossing bridge lowercase a into land area B, then we will have a string that looks like this: A lowercase a capital B. Now the crossing is this part right here. If the area we're currently on, which is capital A, is at the beginning of the bridge string, then the crossing is just the last 2 characters in the string, or everything except the first character, is what this slice says here. That would give us lowercase a and capital B. If, on the other hand, we had something like this, capital B, lowercase a, capital A, we're starting from land area A and we're crossing bridge lowercase a into land area B. So what we need is the first 2 characters, but we want them in reverse order. And that's what this slice does here for us. So once we have our crossing, we can call the makeWalks function recursively. We can give it the new area that we're starting from, which is going to be the last character in the crossing string. We'll update the string of everything that we've walked so far by taking what we have currently and concatenating that with our crossing. And we'll update the tuple of bridges that we've already crossed by putting the bridge we just crossed at the beginning and unpacking anything that was in our original bridges crossed tuple. Now that we've defined makeWalks, we can call it with the original area that we passed to our get walks starting from, and then return the list of walks that we generated. Now, in order to find all possible walks from all 4 areas, we're going to create a dictionary called walks starting from, and we're going to use a dictionary comprehension to build this. Each key is going to be an area coming from the string A, B, C, D. So the first key will be capital A, the second one will be capital B, and so on. And the values for each key are going to be the list that we get from calling get walk starting from with that particular area. Once we've got that dictionary, we can calculate the total number of walks using a generator expression here that calculates the length of all the walks from all the different values in the dictionary. So it's going to take a look at the length of the list we got from this get walk starting from function, calculate the length for each of those, and then sum over all of those lengths to give us the total number of walks. And then finally, we can print that number to see how many total walks there are. And in this case, we see there are 372 walks. And we can take a look at some of those. We could have walks starting from A, and let's just take a look at the first 3 we see the walks looking like this. We start from land area A, cross bridge lowercase a into B, then cross bridge lowercase b back into land area A, cross bridge C into land area C, then bridge D into A, bridge E into D, and bridge F into B. Now we've used bridges A, B, C, D, E, and F, which is 6 bridges. We've not used the bridge G. This walk was unable to cross all bridges exactly once. So now that we've got the 372 possible walks, we need to determine which ones are actual solutions to the Königsberg bridge problem. Now, intuitively, the way we could check this is looking to see whether or not these strings contain a lowercase a, a lowercase b, a lowercase c, and so on for each of the 7 bridges. But that's going to require a little bit of conditional logic, a lot of if statements there, or a big conditional expression to do that. We already know that the bridges are only contained once in these strings because that was a condition. We were only crossing bridges that hadn't been crossed before. Really, we can just look at the length of this string and see if that length comes out to what we would expect if we crossed all 7 bridges. So what would that be? We should see 7 pairs of a lowercase letter followed by a capital letter for 7 different crossings. Each of those contains 2 characters, so that would be 14 characters. And finally, the initial starting land area, which would add 1 more to that, so that would be 15. If any of the strings in our walks contain 15 characters, we know that that string is a solution to the problem. So let's see how we can do that. Let's use a list comprehension to filter out all strings in all possible walks that have 15 characters. Before we can filter all the walks for possible solutions, we need to have all of our walks in a single list. Right now we have them in a dictionary and split up by each land area. What we want is to have them have every single walk in a single list. The way that we're going to do that is using a handy function from the itertools module called chain. Now what chain does is chains together items from an iterable into a single iterable. So you can pass to chain multiple iterables. So you could pass several lists into chain and it will chain all those lists together into a single list. We're actually going to be using a special function on chain called fromIterable. And the reason that we're doing that is because we're going to call the values function on our walks starting from dictionary. Walks starting from .values returns essentially a list of lists of all the different values in our walk starting from dictionary. What fromIterable does is takes that list of lists and basically drops the enclosing list and looks at all the lists inside of that list and then chains those together for us. However, chain returns what's called a chain object instead of a list. So we could convert this back to a list if we wanted to have a list of all walks, but we don't really need to because chain objects are iterable themselves. So we can't iterate over that and pull out all of the walks in that chain of walks that we just created. Now that we have that, we can actually filter them out for possible solutions. So we'll use a list comprehension to do this. We're going to look at each walk in all walks, as long as the length of that walk is exactly 15. And then finally, we'll print the number of solutions that we get. So let's see what happens when we run this. And we see there are 0 solutions. Now this aligns with the solution that Euler came up with. He was able to realize that it was actually impossible to solve the Königsberg bridge problem. Or rather, it was impossible to come up with a walk that used each bridge in the city exactly once. Now we've just done it in just a few lines of Python code and not using any graph theory. But what we've done is given ourselves a tool to generate all of the possible walks. And now we can study those to see what patterns we see, what things we notice, and help us to see if we can solve a more general problem for any configuration of bridges and land areas. And that's exactly what Euler did. He was interested in really the more general problem of any kind of configuration. We've just solved the Königsberg bridge problem in Python using a brute force technique that involves recursion. Now, if Euler saw this technique, he'd probably hate it. It doesn't tell us anything about why there is no solution to the problem. So while it does solve the problem, it's not satisfying from a mathematical perspective. Euler wanted to know under what conditions was a path possible, if there were any conditions like that. And moreover, he wanted to know how you could find a path if the conditions were right for one to exist. Now, some of what Euler did is beyond the scope of this particular video. We'll return to it later in our investigation once we've built up a bit of a more modern notion of what graph theory is. But let's take a look at how Euler determined that there was no solution to the Königsberg bridge problem and compare it to what we've just done. What Euler did, and what a lot of mathematicians like to do when they're trying to solve a problem, is reduce it to a very simple case. So here we've got two land areas, A and B, and 6 bridges, A, B, C, D, E, and F. So we can look at what happens when we have an even number of bridges connecting the two land areas, like we have in this diagram, or an odd number of bridges. Let's take a walk starting from landmass A. We can find a walk here that crosses each bridge exactly once. Now, this could continue on to other land areas, and we don't really care what happens at that point. We just want to focus on this little piece of, say, a larger system. And let's write out this walk using the string notation that we used in our Python program. We start at landmass big A and first cross bridge little a, putting us in landmass B. Then we cross bridge little b, putting us back to landmass A. Then bridge C, putting us on landmass B. Then bridge D to land area A. Then bridge E to land area B. Then bridge F back to land area A. Now let's take a look at how many times each capital letter appears in the path string. The letter A appears 1, 2, 3, 4 times. And the letter B appears 1, 2, 3 times. If you look at the original diagram of the Königsberg bridges, you'll see that each landmass has an odd number of bridges connected to it. For landmass A, we have 1, 2, 3, 4, 5 bridges. Landmass B has 1, 2, 3 bridges attached to it. C also has 3 bridges attached to it, and the same with D. So since we're concerned right now with the Königsberg bridge problem, let's assume that we only have 3 bridges between land areas A and B. And let's go for a little walk. Now we can come up with a walk that crosses each bridge exactly once, and let's write that walk out using the string notation we had in our Python program. Land area A appears 2 times, and land area B appears 2 times as well. Now let's see what happens if we have 5 bridges. Again, we can come up with a walk that crosses each bridge exactly once, and we can write that walk out using the string notation from our program. Now let's see how many times each letter appears. A appears 3 times, and B also appears 3 times. If we had a walk, let's say this diagram was just a small piece of a larger diagram with other land areas and other bridges, then we would still have to cross each of the bridges in the diagram. So our walk would come in from somewhere, say we're not starting on A, and would cross bridge A and would go off somewhere else. At some point, maybe we come in and are at land area B and cross bridge D here and go off somewhere else. Then maybe we come in again through land area B and cross bridge C and go off somewhere else. Then maybe we come in here and do something and come back and cross this bridge and go somewhere else. We don't really care what's happening in these other parts of the walk, because our final string is still going to have to contain the same number of B's and A's. And it's always going to be, in this case, no matter what's going on, we're always going to have the 3 A's and 3 B's. So let's say the number of bridges between two land areas A and B is some number called K. When K was equal to 3, we saw that A appeared 2 times and B appeared 2 times. When K was equal to 5, we saw that A appeared 3 times and B appeared 3 times. Can you guess what it would be if K is equal to 7? Now we could draw a diagram and go through it, but you might be able to guess at this point that A would be 4 and B would be 4. What we'd like to do is summarize this as a function of K, meaning a formula that we have in terms of K that we can use to calculate the number of times that A and B have to appear in our string. Well, if we add 1 to this and divide it by 2, that gives us 4 divided by 2, which is equal to 2, and which is the number of times both A and B appear. We can do the same thing here. Add 1 and divide by 2. That gives us 6 divided by 2, which is 3. 7 plus 1 divided by 2 gives us 4. Now you can argue precisely that this formula works whenever you have an odd number of bridges between two land areas. We won't get into the exact rigor in this video. The key takeaway is this. If there are an odd number K of bridges connected to a land area, then the land area's label appears in the walk exactly K plus 1 divided by 2 times. Now that we know how many times each land area's label has to appear in a string representing a walk, let's go back to the original Königsberg diagram and take a look at how many bridges are connected to each land area and the frequency with which that land area's label must appear in our walks string. So for land area A, we have 1, 2, 3, 4, 5 bridges. And using the formula we came up with, we'll need 5 plus 1 divided by 2, which is 3 times that it has to appear in the string representing the walk. Land area B has 1, 2, 3 bridges connected to it, which means that it has to appear in the string 3 plus 1, which is 4 divided by 2, which is 2 times. Now the same is true for C and D because both of them have 3 bridges connected to it as well. So we know that land area A has to appear in our string 3 times. Land area B has to appear in our string 2 times. Land area C 2 times, and D 2 times as well. Now, what does this tell us about the length of any path that contains each of these bridges exactly once? Well, the length would have to have 3 A's plus 2 B's plus 2 C's plus 2 D's, which is 9. So you have to be at least 9 characters in there. Now, the way we represent paths is we have a starting land area, and then we also include the bridges in the path as well for each time we cross a bridge. So we can assume that one of these 9 appearances is going to be our initial land area, and that the remaining 8 will be associated with a lowercase letter for a bridge. So one of those land areas is our initial land area that starts the walk. And we've got the remaining 8 appearances that we need. Now, each of these has to be associated with a bridge, which means that there's going to be 8 characters for bridges in the string. And we already see a problem. We need 8 bridges in order to have a string that crosses all of the bridges, but we only have 7 bridges. So the fact that we need 8 bridge characters means that one of those bridges is going to be used twice. So this tells us that it's impossible to solve the Königsberg bridge problem in such a way that each bridge is used exactly one time. And this is exactly how Euler solved it, using this method of looking at strings like we did and counting how many times the label for a land area needs to be included in that string. Now, Euler did more than just prove the impossibility of the Königsberg bridge problem in his paper. He actually came up with a method for determining whether or not such a path exists for any combination of bridges in land areas. Now, we're not going to get into the details of the other things Euler did in his paper in this video. We'll revisit it later once we've established a little bit more modern graph theory to talk about it in a little bit different language. Now you might be wondering, what does any of this actually have to do with graph theory? I haven't seen a graph in the entire video. What Euler's solution boils down to is the way that land areas are connected by bridges. There's no notion of geometry whatsoever, no measurement of distances or angles between those land areas. The length of the bridges doesn't matter, and this is really the essence of graph theory. In the previous video of the series, I gave you an example of the kind of graphs we're going to be looking at. It was a collection of vertices represented by dots, connected by edges represented by lines. In the Königsberg bridge problem, the land areas are the dots and the bridges are the lines. And you can actually convert Euler's diagram to a graph. Let me show you how. The first thing we can do to convert Euler's diagram to a modern graph is represent each land area with a blue dot and use red lines to connect two dots if they have a bridge between them. And we'll add one edge for every bridge. If I take away Euler's diagram, we're left with a graph representation of the Königsberg bridge problem. This is known as the Königsberg graph. Euler never drew this, and in fact, this representation of the Königsberg bridge problem didn't show up until the late 19th century. Sometimes I wonder if the townspeople of Königsberg had had Python at their disposal and had written a little program like we did today that brute forced a solution to their problem. Would that have delayed the invention of graph theory at all? Certainly they would have come up with an answer to their puzzle, but it wouldn't have told them why such a solution was impossible. But I don't really think that would have stopped the birth of graph theory. But I guarantee you someone in Königsberg would have been left wondering, but why? It's the curiosity that drives mathematicians to invent new things, to solve problems in new ways, and to continue to push the boundaries of what we even consider mathematics. I really hope you liked this video. If you did, give it a thumbs up and consider subscribing to my channel. I've got lots of more content planned for this series on graph theory with Python, and you can tap the bell icon to get notified whenever I publish a new video. Thanks a lot, and I'll see you next time.